Yeah, so yeah, thanks a lot for the introduction. Thanks a lot for inviting me. Today I'll be talking about generative neuroscene representations for 3D wave image synthesis. And just like it was already mentioned, the papers that I will cover today are first Graph, generative radiance fields for 3D wave image synthesis. And then we will also briefly touch on our newest work, Giraffe, representing scenes as compositional generative neural feature fields. Oh, and by the way, I was told that it's like a very dynamic session, so just feel free to ask questions in between or later. Cool. And so, yeah, these are the great collaborators that I've been working with on these projects. And okay, yeah, let's dive right in. So first off, I think generative models are great. So the usual setup at test time is that you can sample a latent code from your prior distribution, and then you can give this to your trained generator, and you get out pretty amazing generated image these days. So here we show an example from Steigen 2. And then you can sample a new latent code and you get out a new image. Or you can sample more latent codes and you get new images. But here you can ask, is the ability to sample photorealistic images actually all we want from our model? And here I would argue, as many do, that actually what we want is that we have control over the generation process. So from a high level, if we think about possible applications like animation movies, as we see here, or video games, for example, or virtual reality applications, we can see that just generating high quality images is not enough. We want to engage in the scene, right? And we want to manipulate the scene. And so to be more specific, our goal is a generative model for 3D wave image synthesis, which allows us to generate photorealistic images, but then also we want to have control over individual objects with respect to their pose, size, position in 3D. We also would like to be able to control the camera viewpoint. And lastly, in these projects, we consider the case where we train from raw unposed image collections. So this means that you just have a large set of images without any additional information. And in the first project, we analyzed what representation we should use for 3D wave image synthesis. And so there has been a few works on this, and a very popular, very cool approach is called Hologun. It was presented at ICCV 2019. And here, the idea is that you, just as in the normal GAN setting, you sample a latent code, but then you represent your scene or object in a voxel-based 3D latent features. And then you can use neural rendering techniques to get out your final image. And we find that this representation leads to like very high quality images. But if you actually check how multi-view consistent this representation is, we find that it suffers in multi-view consistency. And to be more specific about this, what we did here is that you can basically fix the identity of an object, and then you sample a lot of images of this object from different viewpoints. And then what we mean by this arrow indicating call map, we mean that we then apply like a classical reconstruction method on these many images, right? And this gives you like some indication how multi-view consistent your representation is. Because basically these classical methods like call map, they assume obviously that the scene is multi-view consistent. And yeah, it gives you some indication. Here we see that it suffers in multi-view consistency. And another cool project called Platonic GAN is similar, but also different. So here the idea is that you again start with a latent code, but now you don't have these abstract features, but you have a voxel grid basically with colored voxels. And then you can do some volumetric rendering to render out your image of this representation. So here we find that this is more multi-view consistent, or it is multi-view consistent, but for voxel-based methods, you have this problem that they scale quite badly. And so we find that it leads to low image fidelity. So you don't have that high image quality at the end. And I mean, the reason, probably you're all familiar with it, but the reason why voxels scale so badly is that if you want to increase the resolution, your memory requirements grow cubically, right? Okay, and then finally, what we propose here in overview are generative radiance fields. And so this work is inspired by the great work from Mildner et al. Called neural radiance fields. I'm sure you're all aware of it. And the key idea is, for the representation, is that you learn this function g theta, and it's a continuous function which maps from a 3D location x and a viewing direction d to a color value and a density value at this point for this given viewing direction. And this is a continuous representation. And we find that this leads to more multi-view consistent results, as we see here in this far right image. But we also get high image quality. And compared to voxels, for example, you don't have this scaling issue. So the scenes are represented in this weights of the neural network. So you have a relatively low memory consumption here. Okay, and so let's have a more detailed look at this method. Let's have a look at a forward pass through our method. And I think this way you understand it better. Okay, and so we start off with sampling a camera matrix K and a pose and a patch sampling pattern. So here, to note this camera matrix, we define it per data set, so you actually don't sample it, but you keep it fixed, or you have a fixed camera matrix, the intrinsics basically, and then the camera poses you sample from a distribution that you have to define, right? We will talk about this a little later, but you basically assume some distribution and then you sample from it. And then the patch sampling pattern, we will have a closer look later. Now we give these three things basically to our generator. And then we now sample with the sampling pattern, basically we sample basically patches on the image plane as indicated in this figure here. And the idea here is that we always sample, in our case actually, a 32 by 32 grid. So we always sample a fixed number of pixels, but the distance between these pixels we will sample. And but this we will talk about later. Okay, but now you have pixels or rays that you want to evaluate. And then next, what you do for each of this pixel array, you get a viewing direction dr, and you sample points along this ray that you shoot from the camera through this pixel. And now for each point, you pass the viewing direction dr and the sample 3D location through a positional encoding and give this now to the radiance field. So except for the sampling of the camera pose and this patch sampling, this is very similar to the original NeRF model, right? And so we say conditional radiance field here, so something is still missing. And here the idea now is that we, in addition, what we give the network are two sampled latent codes, a shape and an appearance code. And with these four values, actually with these four tensors, you can then predict the color and density. And this we do for each point along array, and then we do it for for all sample pixels. And then we can do volume rendering just as in the original NERF model. And then you get out this predicted patch now. So basically you get the predicted color values. And then next, what we can do then is sample real images from our data distribution, for example, a large collection of cars, and then apply sample also a patch sampling pattern, just as we do for our generator. And then we can extract real patches now. And then we just pass these real and fake images to our discriminator, our patch discriminator, and we can train our full model with an adversarial loss. And so this is basically then our method in a nutshell. And then two key aspects that I want to highlight here to make this work. First is this is operating on these image patches. And we do this actually to avoid like excessive memory consumption, because while and I think you as well, we are big fans of this neuroscene representations or like something like NERF, etc. But the problem is that if you do volume rendering, you actually need to evaluate a lot of points. So for example, if you sample 100 points along each ray, for a single pixel, you already evaluate the network 100 times, right? And then if you sample a very large image that you want to evaluate, this takes first a lot of memory and then also a lot of time to evaluate. And so we find that having this 32 by 32 grid is in the range where you can train decent, and the memory consumption is still okay to train on a single GPU, for example. But this also means that we cannot provide the full image to our discriminator, right? And here we make use of the continuity of our representation, and we can now sample uniformly, basically the scale of the patch. You can think of it as using dilation. So basically, you always evaluate 32 by 32 pixels, but the distances between these pixels we sample, right? We do it for the real and fake patches. And this way, the discriminator sees the full image in a downsized resolution, basically, downsampled resolution, but it also sees close-ups. Okay. So if there are no questions here, I would then discuss these conditional radiance fields. So how do we actually parameterize these conditional radiance fields here? And first, we just use fully connected MLPs with redo activation similar to NERF. But then the difference is that we concatenate a shape code we sample from our prior to the encoded 3D location. And further, we also sample another latent code, our appearance code, and concatenate this with our viewing direction. So only in this view-dependent branch, basically, where you regress the color value. So here, I think it's important or interesting to note that in theory, the network could cheat, right? So it doesn't have to use, for example, the appearance code. But we find that this just leads to a, I don't know, lazier solution for the network, maybe, that it automatically does this disentanglement of shape and appearance quite consistently, which is quite cool, I think. Okay. And now this sounds cool. Does it actually work? So here we show some results on 256 squared resolution. Here we trained our network on synthetic renderings from the Kala simulator. And on the top row, we show our renderings. On the bottom row, we show the depth maps, which is a quite cool aspect about the representation, that you can render out even the depth maps.
Hi, Michael.
Hey,
Um, Thanks for presenting. Can I ask a question?
yeah, sure, go ahead.
Uh, I'm wondering if you go back to your diagram, uh, which part, yeah, which part does allow you to do the, for instance, rotation?
You say rotation
Yeah.
or? Oh, okay. So the rotation is earlier. So let's have a look at this large diagram here, right? And so the idea is that in the first part, you give the generator a k and this psi, right? Sampled from your, so this psi is the camera pose, right? This you give in, and here in this 3D point sampling, basically, we implicitly show here like the camera center and then the image plane, and then how you shoot the ray through the scene, right? And
Right.
here, basically, then at it's a good point, things actually. So at training time, we just sample this, but then at test time, we have control over this. We can manipulate this.
Okay, so you can say, for instance, represented with some numbers and say that, I want 30-degree rotation, yaw, pitch, whatever. Uh,
Right.
and
So this peak, so this distribution over camera poses
Mhm.
is defined per data set. So for example, for the cars, we assume we see the cars from all sides and also from the front and from the top, basically, and everywhere in between. And so this means that we sample it during training, really uniform on the upper sphere, basically. And then at test time, you can manipulate it exactly. So you can parameterize it with two angles, for example, elevation and rotation. And then at test time, you can do this arbitrarily.
Yeah, you know that we in the stability paper we actually showed that you can do different type of transformations. So this is cool that you do 3D, for instance, here. And I'm wondering,
Mhm.
can you do other type of camera transformation, for instance, here? I suppose by moving your camera, you can shift or zoom.
Yeah, you can change it, right? So we didn't change it over what is sampled during training. So we haven't tested that. But as you learn this scene representation and you really have this 3D representation, you can try out more transformations. Yeah,
Yeah, certainly. Well, in the type of GANs that we talk about, for instance, style GAN or big GAN and this kind of thing, big GAN,
right.
none of them actually explicitly had parameters to
Mm-hmm.
these kind of transformations.
Mm-hmm.
However, the cool thing is that you could get these transformations by walking in the latent space. So now my question here is that have you tried that kind of experiment to see, even though you don't have that specific transformation in your data set, can you do that in your test time? And if so, um, to what extent you can do that?
Mm-hmm. So just as I said, we didn't try it actually. But so if I remember correctly, for example, there's actually currently an archived paper, PyGAN, which do something similar. Just so the setup is similar, and I think they actually do it. So they, for example, zoom in or zoom out or something like this, for example, and
Yeah.
it works to some degree. So I mean, the area which is outside, right, there it can do nonsense. Um, but for like the object, it looks quite consistent. Um,
Mhm.
and I
Yeah, yeah,
think, yeah,
I have seen that's a also good paper. Um, all right, cool. Yeah, the reason that I'm asking this question is that I would like to get your model and ask these questions and run this type of experiments and see what it gives us. But also, you have another paper that you are going to discuss right now.
right, yeah.
I thought that maybe have more. we can do more with that.
Right. Um, yeah, so maybe just to say one final word on this then, is that I think the cool thing and the whole goal is, so we call it like 3D aware image synthesis. So the idea is that you incorporate this 3D representation into your generator, right? And so this gives you a strong inductive bias with like these, where you can manipulate the camera pose, and you could even, as you said, do more transformations than there are in the training set. That's true.
This also allows you to do object-based, like per object transformations. And I'm curious to hear about that part, because the natural question there would be, like, how many objects can you do in one scene?
Right. Okay. Yeah. Let's maybe finish off this project, and then we'll talk about the
Go ahead.
multi-object scenes. So, okay. I think I finished this slide. And then, yeah, exactly. So we started to have a look at the results. So here I just want to stress, so it's quite cool that you learn these consistent, multi-view consistent representations from only a collection of images, right? So we don't use any additional information. We don't assume any multi-view images of the same object, etc. And you get out quite consistent representations here. We also apply to a real-world dataset. In this case, it's the dataset of human faces. Again, we show renderings on top and depth maps on the bottom. And here it also works reasonably well. Here maybe a difference is, just as we discussed before, this camera pose you have to do per dataset, because here in the dataset, you see the human faces only from the front and the side, right? So you couldn't do a 360-degree rotation here. Okay, but so in summary, we propose Giraffe, a novel method for 3D aware image synthesis, and it allows for high resolution, multi-view consistent image generation. It can be trained from raw unposed image collections. A key thing that we saw here is that we can do this patch-based training. Our key idea is to use this patch-based training to avoid excessive memory consumption. And from a more broader perspective, I think we can say that radiance fields are also promising representation for generative tasks. Just actually, as we already mentioned, of course, there are limitations. So one, for example, is that we are limited currently to single object scenes. And also we have this slow rendering time, which we inherit from this volume, like nerve from volume rendering. Okay, and so motivated by these two limitations, in the follow-up project, we investigated how we can now scale to more complex and multi-object scenes. Yeah, from a broad perspective, or a high-level idea is what we did in Giraffe actually is that we incorporated an appropriate 3D representation into the generative model. And now the idea is what we do in Giraffe now is that we incorporate a compositional 3D scene representation into the model. So we further combine this with a neural renderer to yield fast and high quality inference. Okay, let's have a look at the Giraffe model then. Again,
before you move on, can I ask some questions on the graph first?
Sorry, can you repeat?
Before you move on, can I ask questions on the
graph? Oh yeah, sure,
first?
Go ahead.
Okay, so I guess my first question is, it seems like this method and Python have a lot of similarities in the resulting task, but there are a couple implementation differences. So one of them is using the sinusoidal activation. Another one is a concatenation of the latent code versus adaptive instance normalization. And then a third one I think is a difference in the discriminator. Can you speak to like which of these differences do you think makes the biggest kind of like like which of these differences do you think impacts the model the most?
Yeah, right. That's a very good question. And I can't answer it completely because we don't have this side-by-side comparison. But okay, to touch your points. So first, I think, so if I remember correctly, they do some form of progressive growing. And at the end, they don't do this patch discriminator. They always render out the full image. And I think this is probably good, and it gets you better results than a patch-based discriminator. So it's always better to do it on the full image. But it also,
like the memory requirements of that would be massive, right?
Exactly. So I think, for example, we didn't do multi-GPU training. I think they probably had to use multiple GPUs and or reduce the batch size. So I think just using the full image is always better, but it has, so if you want to go, for example, to 512 resolution, which we actually did, then you cannot do it anymore, right? But so I think for lower resolution, this definitely makes sense. So this is the one aspect. And then you said one other aspect was the difference in, also they actually combined your other 2 points, I think. So it's, we use the ReLU network, and they have the Siren network, and then you also mentioned the conditioning. So I think this is very combined. So we just use a very simple conditioning, the concatenation, and they propose this other this other conditioning, which is probably very suited for the Siren network, and it seems to work very well. And they also, I think what they further have is actually to have this mapping network from StyleGAN or StyleGAN 2, where you basically pass latent code first through a few, basically through a ReLU network even, and then use this latent code. So it's very hard to tell where the improvement comes from. So I think this, I think Siren is a very interesting parameterization, right? So I think, I mean, this might be why the results are better. There are actually small differences. So for example, what matters a lot for these methods is how you sample the camera pose, right? If you would sample it very badly, let's assume for the faces, you sample like 360-degree rotation, it would not really work. And I think they changed from a uniform, for example, to a normal distribution. So I'm not sure if this makes a huge difference, but it could also be one difference. Yeah, but I think we even have Vincent here, right? So he can also say a few words on this if he likes to. Yeah.
Yeah, I mean, like Eric, I've talked a little bit about this with Eric, and Katja came by our poster at NeurIPS as well. And Eric basically made the same points that you made. I think one part is that this film conditioning that they use is combined with the Siren gives you an advantage, is just probably slightly more expressive, or is more expressive in the ReLU network. And then he also mentioned the progressive growing as a point that that improved the performance. And then also I think there's always a difference of when you like do a second iteration of a method, right? Like when you
Right.
come up with this basic idea and you just like look at it with a new eye and you set up a new training routine and so on, you always just get like an improvement just by having a fresh pair of eyes look at it. So.
Yeah.
Did Eric comment on like how he managed to feed the whole image into the discriminator?
Well, so I convinced Gordon, our advisor, to buy a very big server some time ago, which has like 4 of these RDX 8000 GPUs, which each have 48 gigabytes of memory.
Yeah.
And so that certainly helps.
Yeah.
I can highly encourage you to do the same with your advisors. It takes some convincing to spend $80,000 on a server, but it's certainly worth the investment.
Yeah. Where's Phil? Anyway, I'll let him know. All right. Yeah. Thanks. Oh, I have another question, by the way, Michael.
Yeah, sure.
So, I think it's quite interesting that, a lot of people are showing like nerve-based representation allows you to render the depth. But to my knowledge, nobody actually evaluates it. But in the Carla data set, you actually can evaluate it, right? Like, did you try to see how good is the depth? Because according to folks from Google, the depth from the nerve model is actually not, like, it's consistent, but it's actually not correct, especially when it comes to the far view. But in this case, you're just modeling this car object. So I think like the situation is, the task is easier, but I still wonder, like, have you guys evaluated the performance or not, or just visualize it?
Yeah, right. So, I mean, our goal is different, right? So we want to generate high quality images. So actually, it's already kind of hard to evaluate the quality of images. And GAN training, you have this FID score or KID score, which is kind of agreed upon. But then how you should evaluate the depth maps, it's really like unclear, right? Because they just have to be real, kind of. I mean, you could do some tricks maybe, but in the GAN setting, it's very hard to evaluate how good these depth maps are. It's a good point, but I think, yeah, we just evaluate it basically visually, and for our purposes is enough. Yeah.
Okay, got it. Thank you.
So I don't remember who asked these couple of questions, but I hope we answered them more or less. Okay, so let's have a look now at a forward pass to our Giraffe model now. And here, the idea is that we now, instead of having this one shape and appearance code, we sample n shape and appearance codes, one for each object, basically. And then with this, we get now n feature fields. So what a feature field is, we will have a look at later. So important here is actually we show now this in RGB color for clarity, but actually you have again a continuous function, but which predicts the density value and a feature. So actually this should be features here, not colors. And then basically, so one important point here is that you learn this in a canonical space. And then next, now you sample now the size and pose for each feature field, and then you can transform your feature fields into into the same scene space, basically. So now you basically arrange your scene here by transforming it from the canonical pose to the shared 3D scene space.
What is the background data set? The last one.
So I mean, this is just a visualization of our method here. And so actually we train on the comprehensive cast data set, and we will see at the end that we just train with the GAN law, so we don't have a separate background. So we have just images of cars.
But also, can you change the pose of the background, or?
Right, so you can, in theory, you could also sample it, but in our case, we keep the background fixed, so that's an important point, yeah. So in one data, in this data set, we keep it fixed. In another one, we actually also change it. They can also rotate the background, but in the cast data set, basically, it's an identity transformation for the background. And for the cars, we sample the poses during training.
Okay, cool.
And then now we combine all of our feature fields into like one 3D scene representation. We composite it. Next, what we then do is that we again sample our camera pose, also from our prior distribution, just as in Graph. And then we can now render perform volume rendering to get a feature image. So here, instead of rendering RGB color values, we now render feature images. And we then pass now this feature image to our neural renderer, which is a 2D CNN. And then this neural renderer gives us the final output of an RGB color value of a specific resolution. And so here, compared to what we saw before, now we can actually train with an adversarial loss on the full image, even on a single GPU. And the key difference here now is that we do this volume rendering on the feature image at 16 by 16 pixels. This is fixed. And we will have a look at the rendering time later. But you see that the GPU requirements and the rendering time speeds up significantly when you do combine volume with neural rendering, basically. And so again, let's have a look at how we parameterize the feature fields. This time, so the figure here is different, the illustration is different, but it's very similar to what we did before. So here, now we show the separate layers. Like again, we use a MLP with rego activation. We have 8 blocks or 8 layers, but it's in principle, it's completely similar. Again, we have our 3 location X, put it through positional encoding, concatenate the shape code, pass it through a bunch of layers, and then regress the density value. And we have a separate feature head this time, where we give in the encoded viewing direction and the sampled appearance code. And then now, instead of regressing RGB color values, we learn feature vector of a specific dimension, in our case 128. So we replace this RGB color head now with a feature head. And another interesting aspect is how do we combine multiple feature fields. So we will see that the composition, scene composition is very simple. So what we do is basically we have, let's say we have n feature fields. They all predict a density and a feature vector at the position X for viewing direction D. And then if you think about how you should combine non-solid objects, it's very intuitive that if you have an overlapping point, basically that you sum up the individual components. So the density becomes the sum of the individual densities at that point. And further, how we combine the feature vector is that we use just the weighted mean. So it's a very simple way of compositing the scenes. Okay, and also let's have a look how well it works. So we will first have a look at single object scenes. And here we will see now that we can manipulate, I hope that you can see it more or less through Zoom, but now we can manipulate the object, but also the background. So here, for example, we show a horizontal translation of the object. Here we show a translation, like a depth along the depth. We can also rotate the object, and we can also change the appearance of the background here. And a subtle, or maybe a subtle thing here is that you do, although we just train with adversarial loss on images of cars, we can see that there's some disentanglement going on, right? So the foreground or the foreground object is disentangled from the background because then we can control these individually. We also look at multi-object scenes. Here we look at synthetic scenes of this clever data set. And again, just as before, we show how we can manipulate individual objects and keeping the other factors still, for example. So I'm not sure how well this is transmitted in Zoom, but in the last example, it will come again. There's a small thing, like a subtle thing going on where we change the background, which is in this data set. So it will come now. Now here we change the background. And in this data set, the background is very similar except for the lighting conditions, which are sampled randomly. And what is interesting is that the neural renderer is actually adapting like specular highlights of the foreground objects according to how the background changes. So maybe you can see it here a little bit, that the reflections are changing. And another more fun example maybe is because we have this, touching the points that we mentioned before, or were discussing before, is that we have this encapsulating of individual objects. We can actually generate out of distribution samples. So for example, here we increase the range now of the depth translation or the horizontal translation over what it has seen in the data set. Or here we even add more objects at test time. So remember that the model has just seen images of a single car, for example, or of these clever scenes of two items in the scene. And then at test time, we can add more objects. It works reasonably well. It definitely makes mistakes here and there, but it's cool that it works in general at all because it has never seen these examples.
So
Okay.
Michael, what do you show to your discriminator?
We show only the generated image. And what it gets as input from the data distribution are also only images, for example, of cars. Here in this setup, basically on the top right, you have the output image, right? It's only a RGB image, and this you give to the discriminator. That's all.
Oh, I see. So it's not. I thought it's a GAN setup. It's not.
Yeah, it's GAN. It's a GAN. So,
but so for real image, what do you show to your discriminator? Also
the full image of a car.
Of one single car.
Correct.
So you don't show the composition, any composition to your discriminator.
Yes, exactly. So actually,
that's cool. That's very cool.
So yeah, maybe this is a very important point. So maybe this is a little bit misleading here then, the figure. So we show this figure here to show how you can add even more objects. But what you do during training is that you sample one car and then you have one car in the output image. And then also in the training data, you have images which contain one car in the background. Okay, so I think this is well left. So another aspect that we wanted to improve upon is the rendering time. And here we can see, probably not really surprising, but still quite cool, that combining this volume rendering with a neural renderer, CNN-based neural renderer, we really get a significant speed up in rendering time. So here you can see that at a 64 squared resolution, the rendering time is already much faster, but it really makes a difference for higher resolutions, where you have this very large rendering time for graph or nerve, etc., or PyGAN and so on. And with this neural renderer, you really get quite fast rendering time. Okay, so now in summary, in the second project, we proposed Giraffe, a novel method for 3D controllable image synthesis. Key idea here is that we incorporate a compositional 3D scene structure now into the generative model. Again, Graph is trained from raw unposed image collections, for example, a data set of single cars, etc. And the cool thing about these models, or this model, for example, is that at test time you have explicit control now over the camera, but also the individual objects. And of course, it's research, so there are plenty of things left to do. For example, one limitation is that we currently looked at quite simple multi-object scenes. So if we want to train on scenes with multiple objects, we only looked at this synthetic scenes. So here, there's definitely, it would be cool to scale to more complex scenes. And probably also in combination with this is that actually this applies to all of these models, is that we currently assume very simple priors over object and camera poses. And this works well for these data sets we look at, but if you want to apply this now to let's say, Coco data set or Kitty and so on, this probably doesn't work anymore because you cannot just sample uniform because it doesn't match your data distribution anymore. And then on a more general note, maybe, I think these implicit or this neural implicit functions, neural scene representations are very cool and very promising. And I think combining this with generative models is quite a cool direction to explore. And that would be it from my side. So thanks a lot for the attention and inviting me. And if you have more questions, go ahead.
Thanks so much.
Thank you, Michael.
Thanks a lot. Thank you.
Hey, so I guess I'll start while other people are trying to come up with questions. So first of all, I feel like the results are quite cool. The compositional stuff is quite important for sure. But there's one thing that is still like bothers me a little bit. Like, what is the motivation to add the 2D neural render? Because I feel like that part, I mean, like it makes sense in terms of computational reasons, because you want to like feed the whole image into the discriminator, or you want to generate the image faster. But then what it could hurt is the consistency when you switch around the camera poses, or something like object poses, right? And I definitely see some of those artifacts in the output video. Like most of the time it would be good, but sometimes like the balls can become cubes when you're switching the object poses. And I think that's because you maybe use the 2D neural renderer. Do you have some thoughts on that? And
right. So yeah, for sure. I mean, this is definitely debatable, I would say. So first, if let's say you want to have a scene of like one background and 3 objects, then just with the current computational power, etc., just now using like 4 nerves basically there would like increase this, right? So currently this would not be really possible, not really possible. And I think actually, so the motivation more of this currently is the aspect that we touched with this neural renderer, that if I sample randomly a background, right, and I sample randomly an object, so basically this can lead to results which are not plausible, right? So for example, if you have backgrounds which are taken at nighttime and at daytime, and then you sample the object, but you don't model the light. So obviously what we actually would like to even have more prior knowledge in there and model this separately. But currently, if you compose multiple objects and you do this independently, then this cannot really scale to like real world data where you have all these complex things going on. So this is one aspect, I would say. Yeah, I think in general also combining it with neural rendering is promising, but it's true that it might suffer multi-view consistency. This is a danger. The other aspect which you can say, which it can do, is actually, let's say, for example, our work graph, the cars you saw, this is on like synthetic data, right? So actually, when you sample your camera poses, you actually even know the distribution, right? Because you know how it's generated. But if you now go to these complex data sets like this car data set, you don't know this anymore. And if you still assume this simple prior, it turns out that these models don't really work well on this data set, for example. And here this neural renderer can also adapt like basically the, how do you say, like the mismatch between the assumption that you do about your camera distribution and about the real distribution, if this makes sense.
Yeah. So so you're saying like this neural renderer part actually like map the generated feature images to the natural image manifold. So it's like helping to make the actually generated images more more like what we will see in our daily life, but it may sacrifice the multi-view consistency.
Right. Yeah.
Does that make
Yeah.
sense? I see. Yeah, that makes sense. Thanks.
Michael, I think that what you are describing is actually very important. So, for instance, one question here is that what if what can you do when you want to figure out the scale of the proportion of the um, or relative scale of the objects? You know, uh, for instance, if I mean cars probably are, if you are using only sedan cars, they are all almost same size. But what if you want to use a car and then also you want to use a cat? How do you figure out the proportions?
Yeah, I mean, I think this touches, from a broader view, this touches on an important aspect that I also mentioned here under the limitations. It's really cool that we can train only on these image collections, but of course this has its limits, right? So for example, as I mentioned in the lower limitation aspect, we assume very simple priors over the object and camera poses out of the size, right? So basically what we do, or all of these methods do, is that you assume some prior on this, which is easy if you know, for example, they are roughly the same size, but it becomes complex, as you say, if you have multiple objects in the scene and they are very different of size, and how do you relate this? I mean, this you would have to incorporate or like hard code, but of course you don't want to do this, right? So I think it's really promising to explore, for example, how this can be learned, right?
Certainly, yeah, of course. Yeah, I think that that's really cool. Thank you.
Thanks.
I have two questions. One of them is, so you sampled a number of objects in Giraffe. So my question would be like, what prevents an individual implicit function from kind of like cheating and doing multiple objects, or like whether it just like single object decomposition is the simplest thing for it to learn. And then my second question is, so like these works are really great, but part of it seems like black magic, in that the only kind of real supervision is a discriminator on just like unposed image collections. So can you comment on the training stability? And then I guess in Giraffe, it feels like you get a boost from doing the rendering at a lower resolution and upsampling it through the neural renderer so that your discriminator can take in a bigger receptive field. Is that accurate?
So these were a lot of questions, sorry. So the last one, yes, this is fully accurate. So this is the boost that we get, correct. And then let's see. So the other really interesting aspect is it could cheat. That's true. I think what I really like about this work, that it works. So we just have a discriminator and we train it with like a R1 regularization, which is like very typical for GAN training. So we really don't have like, I don't know, any fix or something in there, or like hard coded thing, or this cannot go to 0 or something like this. So this we don't do. And so why it works, so let's again assume that we have the setup of a single car in the background, and we rotate the object randomly in the background. For example, we keep fixed, right? So it's just this inductive bias because it sees cars from like all sides. It's just this inductive bias which really leads to this disentanglement. But of course, there are also disentanglement failures. For example, if you go to like more complex scenes, we have, for example, results on churches, and there, so basically it's Elsan churches, where I say maybe the data distribution is more complex even than these cars, and there sometimes it doesn't put a lot of or it puts like a small church maybe as a foreground object, and then it has like another church in the background, which can be a failure mode. But so for these data sets, for example, this car data set, or the general case also for the churches, it works reasonably well. And I think it's just this inductive bias that you match kind of this, how to say, that you match the post distribution, and it just is easier for the network to learn a consistent representation there. And then you had a third point, I think, which I forgot, sorry.
Oh, can you comment on like training stability?
Oh, right.
Discriminator?
Right. So, let me give like a short history. So we started with the graph work, and then we started in the beginning where we had like no clue if this actually works. And there we had to play around with a few settings. And then we just use these settings for the setup here. And then it works actually quite well. So it works quite stable. So actually, yeah, really stable, I would say. We don't experience like crashes, for example, etc. But we have this typical GAN thing. So you should use not a batch size of 2 or 4, right? At least like 8 or 10, or even better, 16 or 32 or something like this. Besides that, we find for us that the RMS prop optimizer works better. And interestingly, maybe like very fine detail, is that we have a higher learning rate for the generator than for the discriminator, because the discriminator is fully convolutional, and the generator, in this case, the combination of these fully connected networks and the 2D CNN, and there we find that it works better if it has a higher learning rate. But in general, I would say training is stable, yeah.
Thank you.
Thanks.
And when are you releasing the code?
Yeah, so I mean, yeah, we are adhering to this double blind thing. Yeah, but so we'll wait until there's feedback from the submission, and then we will upload the code.
Good luck with that. I'm looking forward to using it.
Yeah, thanks a lot. Thanks for the great feedback and great questions.
Thank you. Thank you.
Yeah, so time is up. I don't know, Michael, whether you still have a few time, because I got one more question. And
yeah, sure, go ahead.
All right, so this question will be a little bit meta. So it's not directly related to the projects you presented, but it's definitely like more like the future of this project. So I feel like the history of GAN evolution, for a long time, we trained games on like specific data set, like church data set or faces data set, until DeepMind has this big GAN stuff that came out and trained it on the ImageNet. And big GAN is actually quite cool. Like I think they have some examples of fixing the latent code while only changing the class that the model is conditioning. Then you can actually get the same pose of different animals. And that, so like it sort of shows the magic of generative model when you train it on a very large scale data set. So what are the bottlenecks for like, for example, Giraffe to scale to ImageNet? What are some like problems that we need to solve before we try to have the moment of like, say, big Giraffe?
Yeah, right. So I think that's definitely the way to go. I mean, from a more broader perspective, scaling these scene representations to generative, or like generative scene representations to this very large scale is very cool. So I think, I mean, compared to basically our subfield here, what we consider, the GAN training is actually quite easy. They just need to generate images, right? But then it turns out that the latent space of these networks, which are trained on these very large data sets, have really cool structure. But compared to this, we actually want to have this implicit 3D bias here, right? And this comes with a cost, right? And I think, I mean, here for the cars, so if you think of images of cars, it's quite easy. The car cannot deform. The car can have some position in the scene. It can be rotated. That's basically it. But if you think of ImageNet, there are like so many different objects which can maybe deform. Like, let's take humans, right? They can deform. This is super complex. And this you should model somehow. And I think also what we currently assume, again, touching the same point, but I think this is really a bottleneck, is are these distributions. So the camera distributions, the pose distributions, the size distributions, etc. We currently hand code them, right? And so we can just input like very simple priors. And here I think also like combining this while learning them, for example, could be very promising, I think.
Nice. Okay, got it. All right, do we have more questions or? Okay, if no, then yeah. Thanks, Michael, for giving a talk, and it's very informative, and the results are pretty cool.
Cool,
So,
yeah.
all right.
It was a pleasure, yeah. Thanks a lot.
Yeah, okay, I guess that's it for today's reading group, and thanks everyone for attending. We'll see each other next week.
Thank
Bye.
you. Bye.
Thanks.
Thank you.
Bye. Bye.